Okay, welcome to lecture 40. We're still in unit 6, approximating numerical solutions to ODEs. So today we're going to be using something called a runga kutta method. Okay, so I'll explain what a runga kutta method is, and we'll look at some examples. So firstly, let's recall that for Euler's method, it was derived by taking a linear approximation to this integral above. Okay, so this is quite a few lectures ago now, but basically we had some this integral is this discrete this definite integral rather is some area under this curve f. Okay, and we approximated that using just a linear approximation. And of course that approximation had some error associated with it. And then secondly, we said, well, what if we calculate the area of this small box and a larger box and take the average area in there, and we formed something called the trapezium method. Okay, but that method turns out to be implicit. Okay, so we created a predictor-corrector method, which we call the improved Euler method. Okay, but the basic idea of this trapezium and improved Euler method is that instead of just taking one point on this red F curve here and using that to approximate the area, we took 2 points on that curve and used that to approximate the area under the curve. Okay, but what if we approximated the integral with more steps between xn and xn minus 1? Okay, so we're not reducing the space step h here. We're just increasing the number of points to make that approximation of that integral. Okay, so what if we did this? What if we took multiple points between xn and xn plus 1 and calculated the area between each of these? So we get the sum of some areas here. In this case, 3 parts. Okay, but the steps actually here each of the width of each of these rectangles here is h over 3. But in fact, they don't have to be even steps. You know, you could have something like this where the first and the last steps are small, and the middle step is large, or the first step is large, and the other 2 steps are different sizes. Each of these approximations would give you a different numerical method. But the idea is that if we did this, if we had all these points, we'd have to know the values of xn plus a third h, xn plus 2/3 h, and of course xn plus 1, or 1h. So this construction would produce an implicit numerical method. Okay, but if you recall, we already overcame that using the trapezium method, using a predictor-corrector method. So we can create a multi-step predictor-corrector method. Okay, and that is the idea behind these things called runga kutta methods. So runga kutta methods, we basically have multiple predictions. So if you recall, for the Euler's method, we only had one term here, and this h times 1 term. The rest were gone. If you call for the improved Euler, we had 2 terms. So 2 terms here. I think it was 1/2 times f at xn yn plus 1/2 times f of xn plus 1 y star. But of course, we could generalize that to as many intermediate steps as we want here. Okay. So these things W here, W1, W2, W3, and so on, these are called weights, okay? And they're constants that generally satisfy that the sum of them are equal to 1, okay? Each of the Ki's, so K1, K2, all the way through to K3, K4, K5, these are like the Y stars from the improved Euler's method, okay? They're basically the function, I say evaluated, but actually it's approximated at a point between xn and xn minus plus 1. The number m is called the order of the method. Okay, so the number of these weights here, the number of these k's here, tells us the order. So Euler's method, we only had one term, so that was a first order method. The improved Euler, we had two terms, so that would be a second order method. So for example, if we take m equals 1, so we're looking at our first order method. If we take the weight w1 to be 1, k1 is just going to be the k1 is just the function evaluated at xn, yn, the right-hand side of the ODE. Then we get this update equation for y here. Okay, but you can see that this is exactly just Euler's method. So it turns out that Euler's method is just a first-order Runge-Kutta method. Okay, well, what if we take m equals 2? So we take two terms here, so two weights and two k's. If we take the weights to be even, so w1 equals w2, which is just a half. K1 is, again, just going to be the function evaluated at xn, yn. K2 is the function evaluated at xn plus 1, so xn plus h, and yn plus h times k1. Okay? Well, k1 is this thing f at xn, yn. So if we write out yn plus 1 for this case, we get yn plus h over 2 times f of xn, yn plus f xn plus h, yn plus h times f xn, yn. Okay, but this term here is nothing but the Euler's method, right? This is just an expression of Euler's method. So if I call this term in red here y star, then in fact, I just get the improved Euler's method back. So it turns out that the improved Euler's method is just a second order Runge-Kutta method. Okay. I should point out though that it's not the only second order Runge-Kutta method. So for example, I can choose different weights here. W1 was equal to W2 was equal to half here. I could have chosen 1/3 and 2/3, or I could have chosen, you know, any combination that added to 1, in fact. So the improved Euler's method is just a second order Runge-Kutta method. It's not the only one. Okay, so, well, let's look at a fourth order Runge-Kutta method now. And so here I'm going to be choosing the weights of our k's to be unequal. So you can see here that the first term and the last term here, k1 and k4, the weights are both 1/6 on those. Okay, so the 1/6 times 1 k1 times 1 k4. The two terms in the middle, k2 and k3, their weights are 1/3 or 2/6 or 1/3. So these ones here, we have 2/6, 2/6. So here our weights are 1/6, 2/6, 2/6, and 1/6. Okay. So the fourth order Runge-Kutta method is basically a 4-step process. So if you recall, for the improved Euler method, we had to calculate y star, which was sort of one predictor step. Here we have 4 steps like that, basically. So k1 is just going to be the function, the right-hand side of the ODE, evaluated at the start of the domain, xn, yn. K2 is just going to be a half step, so xn plus a half times h, yn plus a half times h times k1. Okay, so times this thing here. K3 is the same thing, but evaluated at k2 rather than k1. And then k4 is xn plus 1, or okay, here I've written xn plus h, yn plus h times k3. So k3, this line above. So notice that each step depends on the previous step. So k2 depends on k1, k3 depends on k2, and k4 depends on k3. Okay, so this specific fourth order Runge-Kutta method is generally known as the RK4 method. But of course, there are infinitely many, because I can choose my weights any way I want. I've chosen 1/6, 2/6, 2/6, 1/6, but I could split it up in, for example, a quarter each, for example. But this particular expression of a fourth order Runge-Kutta method is just known generally as the RK4 method. Okay, so these two steps in the middle, K2 and K3, are calculated at the midpoint xn plus a half h of this interval xn to xn plus 1. Okay, so why would we want to do this? Because obviously this is a lot more effort than the Euler method or even the improved Euler method, right? The improved Euler method, we only had one of these things, or sorry, two of these things to calculate. Well, it turns out that the local truncation error for this RK4 method is order h to the power of 5, so the space step to the power of 5. So the improved Euler method was only h cubed, h to the power of 3. So this is actually quite a significant increase in the accuracy, h to the power of 5. And the global truncation error is h to the order of h to the power of 4, whereas in the improved Euler method it was h squared. So this is actually a really massive improvement. And for example, if using the improved Euler's method, I half the step size, then I increase the accuracy by 4 times. But for the Runge-Kutta, if I half the step size, then I actually increase the accuracy 16 times. So there is quite a big payoff for this little bit of extra work here. Okay, well, it turns out that MATLAB has these Runge-Kutta solvers built in, or at least a version of it. So it has this thing called ODE45. Okay, and what this is, of course, we can increase the accuracy of the numerical method by decreasing the step size. But of course, that means we increase the computational time as well. So if we decrease the step size, we have to take a lot more steps, so we increase the number of steps we have to take. But it turns out that if we, there are some regions in the domain of a solution to an ODE where you're allowed to take large step sizes. So if things are not changing very quickly, for example, if your function is linear, then you can take a relatively large step size, but if things are changing really rapidly, like an exponential, then you need a small step size to keep the truncation error small. Okay. It turns out that MATLAB solver ODE45 is what's called an adaptive method. So ODE45 will change the step size depending on whether you're in a region where your right-hand side of your ODE is changing rapidly or not. Okay, so if it's not changing rapidly, ODE45 will take a larger step size. If it's changing rapidly, it will take a smaller step size. Okay, so ODE45 is a Runge-Kutta Fellberg method because this person, Fellberg, suggested that they combine the Runge-Kutta method of order 4 and the Runge-Kutta method of order 5 with a variable step size. So in regions where more accuracy is needed, you take a smaller step size and you use the RK5 method. In regions where things are not changing so fast, then you can just use a Runge-Kutta 4 method with a larger step size. Okay, so let's look at an example here. Y prime is equal to negative 2 times y plus x with the initial condition when x equals 0, y equals 1. And we're asked to find a bound for the local truncation error in y1, so the first step in our numerical method of, in fact, the numerical method we're using is RK4 with the step size 0.1, h equals 0.1. So again, we should be able to solve this first order linear ODE initial value problem analytically. So the particular solution of this initial value problem is shown on screen here. To find the local truncation error, so the error each step of my RK4 method, I have to calculate the fifth derivative, right? So let's just go back a few slides here and show you that the, oops, I went too far. Show you that the local truncation error for this method is the fifth derivative of y evaluated at c, where c is between xn and xn plus 1, times h to the power of 5 over 5 factorial. Okay, so going back to my example, I need to take 5 derivatives of this function, which is easy, right? Because we've just got a polynomial, half x, a constant, or you could say that's the whole polynomial, and then an exponential, which of course is easy to take derivatives of all these things. So we can take a first derivative, a second derivative, a third, a fourth, and a fifth derivative. Okay, so the maximum of the local truncation error between the initial condition x equals 0 and x equals 0.1, when h is 0.1. Okay, the maximum of this fifth derivative is equal to 40, so we're looking at the absolute value, so I can get rid of the negative, 40 times the maximum of this exponential on that same domain. Okay, well, between x equals 0 and x equals 0.1, what value of x will make this exponential of negative 2x largest? Okay, well, it turns out that x equals 0 will make this largest, right? Because x equals 0 means we're looking at e to the 0. If I had chosen x equals 0.1, this will be e to the minus 0.2, which is smaller than e to the 0. Okay, so this is e to the 0 is 1, so the maximum of this derivative is equal to 40 when x equals 0. So therefore, the upper bound on the error, and the local truncation error, is 40 times 0.1 to the power of 5, so h to the power of 5, over 5 factorial, so 5 times 4 times 3 times 2 times 1 is 120. So the local truncation error for this problem is really tiny, right? It's 3.3 times 10 to the minus 6. Okay. Now, estimate the global truncation errors, a separate problem here, estimate the global truncation errors for this, this problem here shown above at x equals 0.5 with a step size of 0.05 using the improved Euler method and then RK4. Okay. Well, again, this is something we're going to solve in MATLAB. So we already actually have code to solve this problem using the improved Euler's method. So we'll go and do that now. And then I'll come back and we'll solve this using RK4 as well. Okay, let's go to Octave Online. Okay, so here we are at Octave Online. So this is basically the code that I had previously for my improved Euler method. I'm obviously solving a slightly different problem, a slightly different initial condition with a slightly different step size, but everything else you should be able to follow this, right? From the previous lecture. So the final value of x is 0.5, and then my functions in here is 4 times x minus 2 times y, 4 times x minus 2 times y, 4 times x minus 2 times y. So this is actually pretty much what we did in the last class. So what I'm going to do now is just going to run this and just let's have a look at what the improved Euler method predicts for this particular problem. Okay, great. So when x equals 0.5, improves Euler method, so IEM predicts y is equal to 1.1056. So this last line here. When x is 0.5, y is 1.1056. Okay, well, that's great. Hopefully that is basically the same as what we had in the last lecture, right? So maybe convince yourself that that's true. But now we want to move on to the Runge-Kutta-4 method. So use the RK4 method to find the solution to the same problem. But now we've got these intermediate steps here, these Ks. Okay, everything else is the same so far. We've got the step size, we've got the initial condition. We initialize our vector x, so, or let's say this is all my x positions from 0 to 0.5 in steps of h. I've still got the same initial condition for y, but now I just have to calculate these k's in here. Okay, so, well, first thing I might do is clear all the k's, because every time I go through my loop, I'm going to want to make sure that K1, K2, K3, and K4 are clear so I can recalculate it again. The second thing is I don't really want to keep typing out the actual function here, 4x minus 2y. I'm going to end up typing that out so many times, once for K1, once for K2, once for K3, and once for K4. So after a while, it gets a bit tedious. So I'm going to show you a little trick. Okay, and this is called using function handles. This works in MATLAB or Octave. So I'm going to create a function handle to calculate f(x), y for me. Okay, well, how do I do that? Well, I'm just going to say fcalc, so I'm going to give it a name. Fcalc is equal to this. If you're sending someone an email, you'd say it's Luke at blah, blah, blah. So this at symbol, and then in brackets, x and y. So I've got two variables here that this function fcalc is expecting, x and y, and it's expecting those in that order. Okay, so x is first, y is second. Okay, and what I'm going to do is I'm just going to make this function fcalc equal to my right-hand side of my ODE. So 4 times x minus 2 times y. Okay, so, well, maybe let's just put that over here in the command window. Clear all CLC. If I type out this command here, fcalc at xy 4x minus 2y, if I now type fcalc, let's say 1, 1, this should go 4 times 1 minus 2 times 1 is 2. Perfect. What if I say x equals 1, y equals 2? This should be 0, right? 4 times 1 minus 2 times 2, 0. So I've created my own function here, effectively. That basically just makes it so that I don't have to keep typing out this thing all the time, and it will definitely reduce the amount of human error I can make. All right, so what I need to do now is within my loop, every time I go through my loop, I need to calculate K1, K2, K3, K4, okay? And I'll do that shortly. And then finally, I need to update my y, right? So y at the new step is equal to, well, up here, the y at the old step, so y I minus 1 plus h divided by 6 times k1 plus 2 times k2 plus 2 times k3 plus k4. Okay, so now all I have to do now is calculate these k values here. All right, so again, all I'm going to have to do here, I don't want to output that. All I'm going to have to do here is refer to this fcalc function that I've just created. Okay, and I've got to enter two things. I've got to enter the x value and the y value. So for K1, the x value is x evaluated at the previous step. So x evaluated at I minus 1. The y value is y evaluated at the previous step. So y I minus 1. Okay, easy. So for K2, I have to evaluate x at the previous time step plus 1/2 times h. So I get x evaluated at the previous time step, I minus 1, plus 0.5 times h. Okay, my y is evaluated at the previous time step plus 0.5 times h times k1. Okay, so I evaluate y at I minus 1, the previous time step, plus 0.5 times h times k1. Okay, well, I do the same thing for K3, although that is evaluated at K2, not at K1. And then finally, K4 is at x I minus 1, the previous step, plus h, and y at the previous time step, plus h times K3. Okay, so now if I haven't messed this up, this should work. Let's see. So we just give it a little bit of time to run. Okay, and great, it seems to have worked, right? Here is my x equals 0.5, and here is my predicted value. So let's write that out. At x equals 0.5, the RK4 method predicts y is equal to 1.1036. And so just to compare that to the improved Euler method, when x equals 0.5 for the improved Euler method, we get a slightly larger number. So the question remains, what is the most accurate one? So let's go back to our PowerPoint slides to answer that question. Okay, so again, we've just solved this ODE here, the exact solution shown here, using improved Euler and RK4 on Octave Online. So RK4, here I've actually written out every single step of RK4. So we were taking steps of h equals 0.05, and we found out that when x equals 0.5, we got y was approximated as 1.103639, blah, blah, blah. For the improved Euler's method, it was quite similar, in fact, but when x equals 0.5, y was 1.1056 instead of 36. Okay, so there's a slight difference between the two here. It turns out that when x equals 0.5, if I chuck 0.5 in the exact solution here, so wherever I see x, I put a 0.5, the exact solution is 1.103638. So you can see it's much closer to the RK4 method solution here. So just summarizing that, the approximated value for RK4 and improved Euler at x equals 0.5 are shown in bold here, and the exact solution is shown below in bold. So let's calculate the error for each of these. So the error in the improved Euler's method is the predicted value minus the exact value, which is pretty small, 2 times 10 to the negative 4. Okay, so that in fact is really small. But the error in the Runge-Kutta 4 method is even smaller. It's 10 to the power of negative 6. Okay, and in fact, how much smaller? If I take the ratio of those two things, so the error in RK4 divided by the error in the implicit Euler, well, it's 5 times 10 to the negative 3. So in fact, RK4 is approximately, it's 200 times more accurate than the improved Euler method for this problem. So this was the global global truncation error in this initial value problem. The theoretical result, well, RK4 is supposed to be globally is supposed to be h to the power of 4. Improved Euler is supposed to be h squared. So if I look at the ratio of basically h to the power of 4 over h squared, okay, well, h to the power of 4 over h squared is just h squared, right? If I just simplify this fraction here, I get h squared. H was 0.05, so that's 2.5 times 10 to the negative 3, okay? 2.5 times 10 to the negative 3. So these things are of the same order, okay? This one is twice as big, but it's still of the same order. So it's, yeah, we got a little bit extra from our Runge-Kutta for this particular problem. But the point is, the expected and the theoretical result are relatively close. Okay, so I guess the point here is that the improved Euler method is quite a significant improvement on the Euler method, but in fact, the RK4 method is a significant improvement on the improved Euler. Okay, so you need to be able to know how to code each of these methods and solve perhaps 1 or 2 steps manually by hand for a test situation. Okay, thank you very much. In the next class, we'll be moving on to an example of solving systems of ODEs numerically. Okay, I'll see you there.